Hello, my dear students. In the last class, I explained about the composite sections, how to find the stresses in the case of composite sections. Today, we will discuss about elastic constants, right? See, in the previous chapter, we have discussed the actual deformations of a body when it is subjected to a direct tensile or compressive stress. But we have not discussed the lateral or side effects of the pulls or pushes. It has been experimentally found that the axial strain of a body is always followed by an opposite kind of a strain in all directions at right angles to it. Okay, thus in general there is always a set of following two types of strains in a body when it is subjected to a direct stress. Okay, the first one is primary or linear or longitudinal strain, and second one is secondary or a lateral strain. Means when the load is acting along the line of the axis, such strains are called as linear strain or longitudinal strain or primary strain. But there will be deformations in the opposite directions also. So such strains are called as secondary or lateral strain. Okay, so we will see here now. Let us consider a body of length L. Okay, let us consider this is the body of length L. Okay, width B and depth D. Okay, let the body is subjected to an axial load P. Okay, this is the axial load which is acting along the line of the axis. This is the axis of the body. So this P is acting along the line of the axis. Okay, due to this axial load, there is a deformation along the length of the body. Okay, this strain corresponding to this deformation is called as longitudinal strain. You can see here when there is a load, this is what tensile load, that is nothing but pulling load. So what happens, there will be increase in the length. You can see this is the original length, but after the application of the axial load, that is nothing but tensile load, there will be increase in the length L plus delta L. Okay, you can see here this deformation is called as longitudinal strain or linear strain or primary strain. Means it is along the line of the axis. This means this deformation is when the load is applied along the line of the axis, and deformation also happens along the direction of the load. Similarly, there are deformations along directions perpendicular to the line of application of force. Okay, see here, this is the length. It is along the line of the axial load, this deformation. But you can see here, there will be decrease in the depth, and also decrease in the breadth. So this is in the opposite directions, right? Or it is perpendicular to the line of the application of the force. The strains corresponding to these deformations are called lateral strains. Okay, so it is means it is opposite to the directions of the force, application of the force. See, what you can say is longitudinal strain is always of opposite sign of that of lateral strain. Okay, that is, if the longitudinal strain is tensile, then lateral strains are compressive, or vice versa. Means if the longitudinal strain is compression, then lateral strains are tensile. Okay, so it is always opposite sign. Every longitudinal strain is accompanied by lateral strains in orthogonal directions. Means always longitudinal strain is accompanied by the lateral strain which is in the perpendicular direction. It is right angles to that direction. So this ratio of lateral strain to the longitudinal strain or linear strain is called as Poisson's ratio. Okay, so Poisson's ratio, that is nothing but, how you can write, it is the ratio of lateral strain to the longitudinal strain. Longitudinal strain is also called as linear strain. So Poisson's ratio, how you can define, it is the ratio of lateral strain to the longitudinal strain. Okay, so we will take one more example. So here you have observed change in the depth and change in the width, right, and change in the length. Let us take consider a circular bar of diameter d and length L, okay, subjected to a tensile force P. Okay, here this is applied, a tensile force is applied. So what happens here? Due to the tensile force, the length of the bar increases by an amount delta L. See here, this is the original length and tensile load is applied here. This is the diameter of the bar. So what happens? Because of the pulling force, there will be increase in the length. That amount is delta L. Okay, and the diameter decreases by an amount delta D. So this diameter becomes now capital D minus small d, that is change in the diameter. Similarly, if the bar is subjected to a compressive force, what happened? The length of the bar will decrease by delta L. Here in the case of tensile force, there will be increment, but in the case of the compressive force, there will be decrease in the length by delta L, and which will be followed by the increase of diameter d to d plus delta d. Right, I have not shown that in the figure, so you just assume here. Now this is tensile force, pulling force. Suppose if it is a pushing force, what happened? If the direction is like this, what happened? There will be decrease in the length and increase in the diameter. So every direct stress is accompanied by a strain in its own direction, is known as linear strain. Understood? Direct stress is always accompanied by the strain in its own direction, that is called linear strain, and an opposite kind of a strain in every direction at right angles to it, known as lateral strain. Okay, I think all of you understood what is linear strain and what is lateral strain. Linear strain is nothing but it is the strain which is developed when the force is applied along the line of the axis and deformations are also in the same direction, but there will be the deformations in the opposite directions also. So such deformations or such strains are called as lateral strain. Suppose here this is the application of the load, tensile load is applied here. So there will be change in the length also, means increment in the length, that is along the line of the axis, so that is linear strain. But there is a change in the diameter, so delta d, this diameter, change in the diameter is lateral strain. Similarly, in the previous example, here this change in the length, that is linear strain, but change in the breadth and change in the depth, that is lateral strain. Okay, so just remember these two things. Then Poisson's ratio, when a body is stressed within the elastic limit, the lateral strain bears a constant ratio to the linear strain. That is nothing but the Poisson's ratio is the ratio of lateral strain to the linear strain. Okay, that is here I have written lateral strain divided by linear strain is equal to constant, and this constant is nothing but Poisson's ratio. It is denoted by the symbol 1 by m or mu. Okay, it is called as mu. So these terms you always have to remember. Poisson's ratio, it is nothing but the ratio of lateral strain to linear strain. Okay, let us solve one example. So you will understand what is the change in the length, what is the change in the width, what is the change in the thickness. Okay, see, let us consider a steel bar 2 meter long and 40 mm wide and 20 mm thick is subjected to an axial pull of 160 kilonewton in the direction of its length. Okay, so here 160 kilonewton axial pull is in the direction of its length. Find the changes in length, width and thickness of the bar. Take E is equal to 200 GPa and Poisson's ratio is equal to 0.3. What you have to find here? You have to find change in the length, that is nothing but delta L, and then what is width? Change in the width, that is nothing but change in the width. B, change in the width is nothing but change in the breadth, and thickness, change in the thickness, that is delta T. These things you have to calculate, right? What is given here? Length is given 2 meter, convert into millimeter, 2 into 10 raised to 3 mm. Then width is given, that is 40 mm. Thickness is given 20 mm. Then axial pull is 160 kilonewton. Modulus of elasticity is 200 GPa. When you convert into Newton per millimeter square, it becomes 200 into 10 raised to 3. Okay. Poisson's ratio, that is nothing but 1 by m or mu, that is equal to 0.3. Okay, so how you can find change in the length? What is change in the length? We know deformation. In the last class, I have told about deformations. Deformation is nothing but PL divided by A into E, right? Here, P, what is P? P is 160 kilonewton, 160 into 10 raised to 3 Newton into L. L is the length, that is 2 into 10 raised to 3 divided by A. A is what? 40 into 20, because it is this one, breadth into depth, 40 into 20, okay, into E. E is Young's modulus, 200 into 10 raised to 3 is equal to, when you simplify this, you get 2 mm. This is change in the length. One is done. Next, we'll see how to find change in the width and thickness of the part. This is, what is this change in the length? Is linear strain, because this change happens along the line of the force. But width and thickness, that is lateral strain. So first you have to find what is lateral strain. We don't know what is lateral strain, but we know linear strain. What is the relationship between lateral strain by linear strain? Lateral strain divided by linear strain, that is equal to Poisson's ratio. Lateral divided by linear, that is nothing but mu, correct? Poisson's ratio. So you know Poisson's ratio, you know linear strain, you can find lateral strain. How? Linear strain, that is strain, is equal to change in the length divided by original length. Linear strain, this is deformation. What you got? This is deformation. So deformation is equal to change in the length divided by original length, or strain is equal to change in the length divided by original length. What is change in the length? That is 2 divided by original length is 2 into 10 raised to 3. Original length is 2 into 10 raised to 3. You get this 0.001. Okay, this is linear strain. So mu into linear strain, that is equal to lateral strain. What is mu? Mu is equal to 0.3 into lateral strain, that is into linear strain, that is 0.001. You get this. This is now lateral strain. Now you know change in the width, that is nothing but lateral strain. So how you can write lateral strain? That is nothing but change in the width divided by original width, right? So we want change in the width, so that is nothing but lateral strain into width. So that's why I've written here change in the breadth is equal to B into lateral strain. So simplify, you will get this. Similarly, if you find the change in the thickness, what is that? That is also lateral strain. So lateral strain is also equal to change in the thickness divided by original thickness. Correct? We want this delta T. So delta T is nothing but lateral strain into T. So T, if we know T into lateral strain, that is lateral strain is this into 20, you get this answer. So like this you can calculate what is the change in the length, what is the change in the diameter, change in the width and change in the thickness. Okay, we'll solve one more example in the next class. Thank you.